Good morning. This is our lecture for Wednesday, July the 15th, 2020. And last time we finished a general discussion of the different colligative properties. Today we're going to focus our attention primarily on freezing point depression and boiling point elevation. It turns out that both of these are at either end of the liquid range for any particular solvent. And so therefore, this is a really nice way to close out our conversation and tie it together with the idea that Chemistry 112 focuses a lot of attention on aqueous solutions, typically of electrolytes. So, we talk about freezing point depression and boiling point elevation. We recognize that just like any colligative property, the extent of the colligative property is directly proportional to the number of particles that are in the system. In order to determine the number of particles that are in the system, we typically choose to work with the concentration unit of molality rather than molarity. This is because molality is a concentration unit that is unaffected by temperature. Typically, if we change the temperature, the molarity of a solution can change because as we either apply heat or remove heat from the system, the volume of the solution can either expand or shrink. And so temperature does have an effect on molarity because molarity relies on volume. But when we talk about molality, the number of moles is not going to change and the kilograms of solvent are not going to change. And so when we talk about the fact that the extent of the colligative property is directly proportional to the number of particles that are in the system, we can use the molality to figure out how many particles there are in that particular system. And so freezing point depression is typically represented as delta T sub F, the change in the freezing temperature. And we typically want to calculate this value so that it will end up being positive. And so because we are seeing a freezing point depression, the final value is going to be less than the initial value. And so just for freezing point depression, we go ahead and we subtract the freezing point of the solvent minus the freezing point of the solution. And so that is T sub F for the solvent minus T sub F for the solution. And so a minus a smaller number is going to give us a positive value. For boiling point elevation, we find that the extent of the boiling point elevation directly proportional to the number of particles. And so boiling point elevation, calculated as delta T sub B, is going to be the boiling point of the solution minus the boiling point of the pure solvent. And so the idea here is that we always want this difference to end up being a positive value. Now, if you're in a hurry on a test and you forget to go ahead and calculate them so that you get a positive value, it's no problem. Just go ahead and turn it into a positive value. And we want to recognize that both delta T sub F and delta T sub B are proportional to the molality of the solution. Back in chapter 5, when we talked about the proportional relationships between pressure and volume, pressure and temperature, volume and temperature, in order to turn that proportionality into an equivalence, what we did was we went ahead and we instituted or included a scaling constant. And so the scaling constant that we include here, just represented by a lowercase k, and we have k sub F, and we also have k sub B. And so by introducing the scaling constant, we now turn this proportionality into an equivalence. Now, we also talked about the Van't Hoff factor last time. So we do need to recognize that we've got to include the Van't Hoff factor as well. For non-electrolytes, the Van't Hoff factor is equal to 1. So when you did your calculations for the freezing point depression with urea, you didn't have to worry about including any value because anything multiplied times 1 is just going to be itself. And so when I is equal to 1, that doesn't change the overall final calculation. But if we work with electrolytes, which is what all of the unknowns were, your unknown salts were all electrolytes, all of which dissociated in solution to give more than just one particle. In those cases, we did have to include the value of I, the Van't Hoff factor. Okay. Case of F is called the cryoscopic freezing constant. And it turns out that every solvent has its own case of F value. In your textbook, these are included in table 13.6 on page 560. You'll notice that I've gone ahead and highlighted both benzene and water because those are the examples that we usually use for solvents. Benzene is an excellent organic solvent because it is, after all, nonpolar. Water is an excellent solvent because we can use that with all of the polar solutes that we work with. So the cryoscopic freezing constant in case of F is different for different solvents. For water, it's 1.86. For benzene, it's 5.5. Oh, wait, I'm sorry. For benzene, it's 4.9. Right? You don't have to memorize those numbers. They'll always be given to you on a test. At the other extreme, we have Kb. Kb is what we call the abelioscopic constant. It is at the boiling point end of our range. And it too is different for different solvents. So again, table 13.6 on page 560. This shows several different solvents, their case of F values, their case of B values, as well as the freezing point and the boiling point. Okay. So we'll do some calculations in a few minutes just to make sure that everybody's comfortable with this. But before we do that, we want to go ahead and talk about what the effect of adding a solute to a solvent does. The addition of a solute to a solvent expands the liquid phase of the solvent. And we can also see this shown for us in figure 13.24 on page 560. So up at the top of the page, figure 13.24, we'll notice that we have the phase diagram for water, and we see the effect of the freezing point depression. The boiling point gets lower. We also see the effect of the boiling point elevation. The boiling point goes higher. And so what happens is the liquid range of that particular solvent is thereby expanded. So let's draw that to make sure that everybody is comfortable with it. So our phase diagrams obey Gay-Lussac's law. Pressure on the y-axis, temperature on the x-axis. We have the boundary between the solid and the gas phases. And then we also have the boundary between the liquid and the gas phases. And so solid, liquid, gas, or if you prefer vapor. And then of course, out where we have the critical point, the distinction between gas and liquid disappears. We then only have one phase. We call that the critical fluid. But our focus right now is back in the world of 1 atmosphere of pressure. If we traverse all the way through the temperature range, we have the boiling point, the melting point, and the boiling point of our pure solvent. If we add solute to this mix, then we end up expanding the liquid phase. The freezing point is depressed, and so we have a different melting point for the solution than we had for the pure solvent. The same thing also holds true at the boiling point elevation end of this curve. The boiling point elevation means that we have a boiling point at a higher temperature. And so the melting point of the solution is lower, the boiling point of the solution is higher, and the net overall effect is that we have expanded the liquid phase for this particular solvent. That is how we can recognize that boiling point elevation and freezing point depression are intimately connected. All right. So in a second, we're going to do a calculation just to make sure everybody's comfortable with that. Let me get these pictures. All right. So, y'all have some experience working with aqueous solutions. Let's go ahead and work with a solution with benzene. Benzene is a nonpolar solvent. We've seen it represented a number of times now. Here we want to recognize because this is a hydrocarbon with a chemical formula C6H6. That means that it is going to be a nonpolar substance. It is a liquid. It works very nicely as an organic solvent. The chemical that we're going to dissolve into benzene is naphthalene. Now, you may actually be familiar with the smell of naphthalene because naphthalene is what is used in mothballs. So if you know the smell of mothballs, you know the smell of naphthalene. Naphthalene is an interesting chemical. Because it's essentially two benzene rings that share a common side. And so naphthalene also is nonpolar, like dissolves like. Naphthalene dissolves very nicely into benzene. And so let's work with a solution that is 2.47 molal. Now, based on this, we want to calculate both the freezing point and the boiling point for benzene once we make a solution of naphthalene and benzene. And so we're going to use the equation that we just made a moment ago, that the change in the temperatures is equal to the molality times the K values. And so for benzene, let's get those values. Benzene has a KB value of 2.53. And benzene has a boiling point of 80.1 degrees Celsius. The KF value for benzene is equal to 4.90. And the melting point of benzene is equal to 5.56 degrees Celsius. Okay. And I'm sorry, I need to go ahead and put the units in here for us. The K expression, or the K units, are degrees Celsius per molal. so the equations that we're going to work with, delta T sub F is equal to K sub F times M. Delta T sub B is equal to K sub B times M. In both of these cases, naphthalene is a non-electrolyte. Therefore, we would expect naphthalene to have a Van't Hoff factor value of 1. And so, for naphthalene, the Van't Hoff factor value is equal to 1. So, we don't need to put it in there. It's just understood. Times 1. Now we just fill in the information. The freezing point difference, 4.90 degrees Celsius per mole times 2.47 mole. And for KB, it's going to be 2.53 degrees Celsius per mole times the molality, 2.47 mole. And so we just need to do this arithmetic. And so our molality units cancel out. We're left with units of degrees Celsius. That's what we hope for, because this is telling us the freezing point depression. So delta T sub F is equal to 12.103 degrees Celsius. Delta T sub B, that's our boiling point elevation, is equal to 2.53 times 2.47. 6.2491. And again, we just have units of degrees Celsius. Now, students often stop at this step because if you do these calculations, the people who make tests list those as actual possibilities for the freezing point and the boiling point. But that's not what we've calculated. We've calculated the freezing point depression. We've calculated how low the freezing point can go. And so we still have one more step. We have to go ahead and subtract this value from the freezing point of pure benzene. And so we have 5.56 degrees Celsius minus 12.103 degrees Celsius. So we have to do that arithmetic. And when I do that, my calculator gives me negative 6.543 degrees Celsius. So that's the actual new freezing point. We have to subtract the freezing point depression from the regular freezing point. And because our freezing point is accurate to the hundredths place, we can report this answer accurately to the hundredths place. And so what we end up with here is an error on my part. I apologize. We have 3 sig figs in 4.90 and 3 sig figs in 2.47. Therefore, we only have 3 sig figs of accuracy once we calculate delta T sub F. And so in actuality, it's not the starting freezing point for benzene that we have. It's the fact that 12.103 is only accurate to 3 significant figures. And so therefore, when we do the subtraction, we can only report that answer to the 10th place. And so the new freezing point would be negative 6.5 degrees Celsius. That is the freezing point of a 2.47 mole solution of naphthalene and benzene. Right? Now, we still need to do the same thing for the boiling point. So the boiling point of benzene starts off at 80.1 degrees Celsius. We want to add the boiling point elevation, 6.2491, also degrees Celsius. When we add these together, my calculator gives me 86.34 91 degrees Celsius, and then 3 sig figs and 3 sig figs means that the result of that calculation, multiplication and division, accurate to 3 significant figures. The number 80.1 is only accurate to the 10th place. This answer would be accurate to the hundredths. And so we find that we're going to restrict our answer based on the number that extends the fewest places to the right for addition and subtraction. And so this answer can only be accurately reported to the 10th place. And so the new boiling point for this solution is going to be 86.3 degrees Celsius. And so my main reason for working this problem with you is because on a test, I've seen it happen many times. Students figure that once they calculate the freezing point depression or the boiling point elevation, they're done. But they are asking us specifically to determine the freezing point of the solution and the boiling point of the solution. And so that's what we have to be able to do. All right. One last thought from chapter 13. We're going to revisit the idea of the Van't Hoff factor one last time. Based on the number of component ions in either an acid or a salt, we have a predicted Van't Hoff factor. What we find out is that many times the predicted Van't Hoff factor is smaller than the observed Van't Hoff factor. Oops. Of course, I got that backwards. What we actually observe, I apologize, is less than what we predict. HCl is an excellent example. Based on the fact that there are 2 parts to HCl, we would expect that if I start off, and let's go ahead and use molality now. If I started off with 1 molal HCl, then I should get 1 molal proton and 1 molal of chloride ion. And so we would predict that I is equal to 2. However, when we go and we make measurements, we observe that the Van't Hoff factor for HCl is only equal to 1.9. Now, you're probably thinking the same thing I did the first time I saw this. 1.9, 2, aren't they essentially the same number? I mean, they round off very nicely. They're within plus or minus 5% of each other. Well, the problem is that in this particular instance, 1.9 is not equal to 2. And so we have to be able to explain why it is that in an aqueous solution, we actually see fewer particles than we actually expect. I mean, it makes perfectly good sense. For every HCl that dissociates, we're going to get 1 proton and 1 chloride ion. So for every 1 proton, there should also be 1 chloride. There shouldn't be any ambiguity there. But when we make measurements, it turns out that there are only 1.9 molal particles in the mixture. So the question becomes, where do those other particles go? Well, the answer is intimate ion pair formation. We need to remember that even though these spheres of hydration protect the ions and prevent them from rejoining back together and forming a new formula unit, when they are bumping into each other and being jostled around, we can actually distort those spheres of hydration. And so if I have a proton and I have a chloride ion, they're surrounded by spheres of hydration, that definitely prevents them from rejoining and making an HCl formula unit that would fall out of the mixture. But if they just bump into each other, and what they've basically done is they've squashed, they've distorted that sphere of hydration between the two of them, then just for a very brief moment, they are rejoined back together. And so being rejoined back together means that instead of two particles, they're now only one particle. And so the formation of these intimate ion pairs is what removes, not a lot, but a few particles from being able to be part of the mixture. And so on average, at any given point in time, about 1/10 of our HCl units are enjoying this intimate ion pair formation. And so this is how we can explain why we see that the observed Bantoff factor is oftentimes less than the predicted Bantoff factor. So we remove those ions from consideration, the Bantoff factor actual value drops. All right, that's everything that we have to talk about from chapter 9. And so we're now ready to switch gears completely. We're going to start talking about kinetics. But before we get to kinetics, there's a few things we need to remind ourselves of. So let me get a picture of these two board panels, and then we will begin our pre-kinetics discussion. When a chemist begins to analyze a chemical situation, there are three big questions that they are trying to answer. Those three big questions are: question number one, what happens? Question number two, how fast? And then finally, question number three, how far toward completion does the process go? And since we typically write our chemical equations, reactants to products, products are on the right-hand side. Another way to phrase that question would be, how far to the right does that reaction proceed? How close to becoming completely products do the reactants become converted? Now, it turns out we already know how to answer question number one. In chapter number 3, we learned about stoichiometry. Stoichiometry is very important to chemists because stoichiometry tells us what the ratios of the reactants to the products are at any point in time that we want to make the measurement. Now, last week, we talked about the idea of state functions. It turns out that stoichiometry can partially be thought of as a state function, because if we only pay attention to what we start with and what we end up with, then basically we're only making the measurements at 2 points in time. How we proceed from reactants to products, not really that important from the perspective of what happens stoichiometrically. So stoichiometry allows us to use those empirical molar coefficient sets to determine exactly how many reactants and how many products we have or we expect to have in any given situation. In chapter 4, we learned about the 5 types of chemical reactions. The 5 types of chemical reactions gave us guidelines that allowed us to predict the products. So, question number 1, what happens? Stoichiometry, 5 types of chemical reactions. We're actually at 2 more today. Question number 2, how fast? How fast will the conversion go from reactants to products? There are actually 3 answers to this question, and we have to pay attention to each one. One answer is instantaneously. We see these types of reactions from time to time. If you set a match to a very dry piece of paper or a dry leaf, it immediately begins to burn. If you drop an Alka-Seltzer tablet into water, it immediately bursts into bubbles. If you drop sodium bicarbonate into any type of acid, it will also immediately burst into bubbles, but the bubbles there are different from the bubbles that were made in our first reaction. And then finally, back in Chemistry 111 lab, we dropped pieces of metal into acids. The metals that reacted did so almost immediately. And so instantaneously is one answer to how fast. Another answer would be moderately quickly. Not instantaneously, but we know, for example, eventually food will begin to spoil. We put it in the refrigerator to try to slow that process down, but even food in the refrigerator will eventually spoil to the point where if we haven't eaten in time, we have to throw it away. So food spoiling on us is an example of a moderately quick, fast reaction. Another example of moderately quick would be rust formation. If you throw a piece of iron out into your backyard, it may not have rust on it tomorrow morning. It might not even have rust on it next week. But somewhere over the next month or so, the rust will begin to form. And once the rust does start to form, then the piece of metal rusts very, very rapidly. But that is an example of a reaction that doesn't necessarily occur instantaneously, but it does occur moderately quickly. Final answer are reactions that go imperceptibly slowly. We'll learn more about this later in the semester, but at this exact moment, the diamonds that are here at the surface of the Earth are very gradually changing into graphite. Given enough time, a piece of diamond will eventually turn into just a piece of pencil lead. And so this process, although it takes many, many, many years, scientists do know that it's occurring. It won't happen within a human lifetime, but then neither will the radioactive decay of something like uranium-238. Uranium-238 has a half-life of 4.6 billion years. If that doesn't mean anything to you right now, it will eventually, because half-life is also tied in with how we keep track of how fast reactions occur. So reactions like the radioactive decay of uranium-238, the conversion of diamond into graphite, these processes go imperceptibly slowly, right? And then finally, question number 3. We've actually just started to scratch the surface about those types of reactions. When we recognize reversible processes, those are processes that do not go all the way to completion. However, most of the reactions that we have run in labs so far do go all the way to completion. In the kinetics experiments, you are timing the decolorization of the blue dye, and we wait or we measure until the blue dye completely decolorizes. That is a reaction that goes all the way to completion. So most of the reactions that we do work with have gone all the way to completion. The experiment that you're going to do Monday next week, that experiment is going to involve chemical reactions that do not go all the way to completion. And so how far to the right will a reaction go? Well, either completely or only part way. And when we start to talk about these reactions that only go part way to completion, this is where we have reversible processes. So, how fast? We're going to talk about this in this chapter, chapter 16. How far to the right? That's the rest of the semester, chapter 17 to 21. So, these are the big three questions the chemists try to answer. Now what I'd like for us to do is just talk a little more detail about the 5 types of chemical reactions to make sure that everybody remembers what we need to remember about those. So back in Chemistry 111, we learned about 5 different classes of chemical reactions. Based on the reactants that we start with, we can identify what type of reaction is actually occurring. So the first of these were what we call the single replacement reactions. Single replacement reactions can be identified because they start with one element and one chemical compound. Now I'm just going to use the letters A, B, and C here. The B and the C do not refer to boron and carbon. They are just any atom type. And so element A, chemical compound BC. And in this reaction, typically A replaces B, single replacement. And so on the product side, B is now by itself. And we have the new chemical compound AC. Now, we called that cationic replacement. It is also possible for anionic replacement to occur. In that situation, instead of replacing B, the cationic portion of the compound, A is going to replace C, the anionic portion of the compound. And so on the product side, we get element C, now by itself, and new chemical compound, EA. And so we can identify these single replacement reactions based on the fact that we start with one element and one chemical compound, and we can predict what the products are going to be if we expect cationic versus anionic replacement. The second class of chemical reactions are called double replacement reactions. In a double replacement reaction, we start off with 2 chemical compounds. And in this reaction, there are 2 replacements. A replaces C, B replaces B. And so on the product side, we get new chemical compound AB and new chemical compound CB. And then, of course, these types of reactions fall into 2 broad categories. They were either precipitation reactions or acid-base neutralization reactions. So those are double replacement reactions. Identifiable, start with two chemical compounds. Third class is direct combination. In a direct combination reaction, we start off with elements and they combine to form a chemical compound. So we use the example of hydrogen and oxygen combining to form water. We're going to do that again today a little bit later. That is an example of direct combination. The fourth type of chemical reaction is called decomposition. These are the ones that are the most difficult to predict. Years ago, we used to spend a lot of time trying to make sure that undergraduates could do these types of predictions. It's kind of given way to other important aspects of chemistry. So we don't necessarily expect you to be able to predict the products here, but we do want you to be able to recognize that it's a decomposition reaction. And so in these types of reactions, we start off with a single chemical compound, and then sometimes through the application of gentle heat, sometimes just on its own, the chemical substance will start to decompose. And when it does, there's no telling what products we might actually get. But the bottom line is the products themselves are going to be some mishmash of what we started off with in our original chemical compound. And then finally, the fifth type of chemical reaction that we worked with was called combustion. And because most of the time we went ahead and formed carbon dioxide and ignored the formation of carbon monoxide, we call that type of combustion reaction a complete combustion. And so in a complete combustion reaction, we have a hydrocarbon, so I'll just represent that C sub X H sub Y, reacting with oxygen from the air. And then if we provide a spark, it will ignite. And the products that we get from a combustion reaction are carbon dioxide and water. And so that's how we can use the different classes of chemical compounds to try to predict what products we would expect. All right. So now we're going to go ahead and focus our attention on answering the second question. How fast? How fast does the chemical reaction occur? Well, three choices: instantaneously, moderately quickly, imperceptibly slowly. And so this is the topic of chapter 16. Chapter 16 is entitled Kinetics, Rates and Mechanisms of Chemical Reactions. By definition, kinetics is the science that studies the rates of chemical reactions. And so the rates are just how fast? How fast is that reaction? Now, the word kinetics automatically implies motion. In fact, I shouldn't say implies. It denotes motion. And it turns out that motion is necessary for collision. Further, chemical reactions cannot occur if there is not collision. Now, these three statements taken together are a very nice description of the theory that regulates how fast reactions occur. We call it collision theory. And so, in order for chemical change to occur, there has to be collision. The collision comes from the motion. The motion is denoted by kinetics itself. And so it's just like eventually meeting your perfect soulmate or your perfect significant other. You got to get out there and you got to bump into a lot of other people before you finally find the one that's right for you. And so collision theory tells us the same thing. There are a lot of collisions that are out there occurring between the different chemical particles, but in order for there to be a successful chemical change, there has to be something special about those collisions. So that's where we go next. So collision theory lays the groundwork for us. Now, we need to figure out what exactly would cause these collisions to be successful. So as long as we're above the temperature of 0 kelvins, we expect that collision is going to be occurring. But in order for the chemical change to be effective, we have a situation where we have to have a successful collision. So not every collision is successful. Therefore, we have to find a way to understand how these collisions would be successful. And so the collisions themselves have to have enough energy to break the bonds that are holding the reactants together, but it can't be so much energy that the atoms would bounce off of each other before new bonds could begin to form that will eventually become the products. So collisions with enough energy to break the bonds of the reactants. But they also have to have little enough energy that the atoms themselves can remain in contact long enough to start to form the bonds that would make the products. And so what that boils down to is that there is a very narrow range of energy that would give this type of a successful collision. Right? Now, in addition to having the right amount of energy, it turns out that the particles also have to be oriented correctly. And so I'm sure you've watched the pre-lab video already. You've seen the situation of what I call the cinematic kiss. In order for the cinematic kiss to be effective, these people have to have been separated for a long time. They have to have not seen each other. Coincidentally, they're both in the exact same region at the exact same moment. Hollywood usually makes it a nice flower-strewn field. They spy each other, even though they're several hundred yards away, and then they start to move towards each other. And as they get closer, Hollywood always slows it down into slow motion, but they embrace and they kiss. They have just the right amount of energy, but they also had to have the proper orientation. And so in the pre-lab video, we talk about if they get too close and all of a sudden they're not very attractive, one might run away. So the orientation is also important, not just the energy. We don't want them running into each other and falling down. We want them to be able to embrace face to face. Now, another analogy that we can use here is breaking glass. It's happened to all of us at some point in time. We have a glass, we're holding it in our hands, and for some reason we drop it. As it starts to go towards the floor, we just stand back in horror, waiting for it to crash and break into many pieces. And then all of a sudden it hits the ground and it just bounces harmlessly away. The reason the glass did not break in that particular instance was because it didn't have the proper orientation. If the glass had had a different orientation, it might have broken when it hit the ground. We also know from personal experience that there is a height above the ground that no matter what the orientation is when you drop the glass, it's always going to break. So there is an energy consideration as well as an orientation consideration that is necessary for a successful collision. And so, second factor, proper orientation. First factor, right amount of energy. And that right amount of energy allows for the bonds of the reactant to break, the bonds of the products to begin to form. And so what we find is that the rate of a chemical reaction is directly proportional to the number of successful collisions. And so that is our guiding principle. How fast a reaction occurs depends on how many successful collisions between the particles can actually be made to occur. So now let's go ahead and talk about a chemical reaction that we might expect to occur because the necessary ingredients are around us all the time. And yet the chemical reaction never does occur. So the direct combination reaction between hydrogen gas and oxygen gas to make water is around us all the time. There is hydrogen in the atmosphere. There is oxygen in the atmosphere. The particles themselves, the molecules themselves are colliding with each other constantly, and yet there's no rain falling out of the sky. There is no water that is forming. And so the question we have to ask is why not? Now, we have a balanced chemical equation here, 2H2 plus O2 to make 2H2O. Since we are also trying to get you used to thinking about the energy requirements of these chemical reactions, let's recognize that the enthalpy for this particular reaction is equal to negative 285.7 kilojoules per mole. The negative sign tells us that this is an exothermic process. We also need to recognize that this is kilojoules per mole. And so because we make 2 moles of water, stoichiometrically, that means that we would need or we would release twice as much energy with this reaction as well. So we write it to make 2 moles of water. We have a value for the enthalpy of the reaction for kilojoule per 1 mole. With 2 moles of water, we would double the amount of energy that would come out of this system. That's not our focus right now, but that is how we could use the stoichiometry of the reaction itself. Now, in order for the hydrogen and the oxygen molecules to form water, it turns out that they require a very specific orientation. First of all, they have to be flat in the plane of the board. And then they have to be squeezed together just right. If they are squeezed together just right, then we enter a situation where the bonds between the reactants are breaking and the bonds between the products are starting to form. And so reactant bonds are breaking. Product bonds are starting to form. And the entire species is very stretched out. So we've collapsed it, and now it's beginning to open back up. If it has the right amount of energy, all of these atoms will stick together. This particular portion is what is referred to as a transition state. It is midway between reactants and products. It is where we are transitioning from reactants to products. Oftentimes to designate that, they put the Easter seal symbol up in the upper right-hand corner. So this is our transition state. Now, from this point, we can either go back to the reactants or we can move forward and make the products. So if the energy is right for this particular orientation, which is required, then when everything is over and done with, 2 water molecules will have been produced that then go ahead and swim away. Now, this reaction barely happens at all at room temperature. That superscripted 0 above the delta H, we call that delta H naught. The naught tells us that we are working under standard ambient thermodynamic conditions. And so that's room temperature. This reaction barely occurs at room temperature at all, partially because the orientation is very difficult to achieve, but at 25 degrees Celsius, the particles aren't moving very quickly relative to higher temperatures. And so as they bumble along, they may or may not get into this perfect orientation. Now, the other aspect of this we want to pay attention to is, at higher temperatures, water forms almost immediately. The energy barrier is overcome, and because the particles are moving faster, they are more likely to eventually assemble into some sort of an orientation that would work. So I always tell the story about when I was a kid. One of our field trips that we went on was to the the Houston Museum of Natural History, where they had this really neat display. It was basically like a 5 or 10 gallon aquarium. It had a wire draped across the top, and there were little fans on the top and on the bottom. Hydrogen was pumped in from one side, oxygen was pumped in from the other. The fans mixed everything together. And then after a certain amount of time of waiting, you would press a button and an electrical discharge would go across the wire, and water droplets would form all along that wire. We had given enough energy, but also enough particles with proper orientation that we were able to make water at that temperature. This happens all the time because what they were trying to approximate for us was the temperature of a lightning strike. And so in the sky along a lightning strike, water molecules are formed all the time, but of course the temperature is close to 3,000 degrees Celsius. So here on Earth, we don't see this happen very often. And the main problem with water not forming from this particular reaction has to do with the fact that we don't get the proper orientation very often. So energy and orientation are necessary. Dropping a glass, whether or not it breaks, having hydrogen and oxygen combined to form water. All right. So now we want to recognize that a rate is a speed. And in your textbook, they do an example on page 694. And they talk about the one-dimensional motion along any straight line, which we can then put in the orientation of the x-axis. And so if we have a particle that travels, we go ahead and arbitrarily make the direction of travel the x-axis. And so there is an initial position and a final position. The change in that position is just final minus initial. And then how long it takes for the particle to go from its initial to its final position is just delta t. And so we have a rate or a speed that would be in terms of, say, meters per second. Now, when we measure the rate of a chemical reaction, we are also measuring a change in the amount of reactant or product. And so it turns out that it doesn't matter which one we choose. We'll talk about why we make those choices in a little while. But we're looking for how the reactant or the product changes with time. And so most of these initial or original chemical reactions that we work with are going to be done in aqueous solution. So therefore, we can measure the rate of the molarity change. So if we have a chemical reaction where the reactant turns into product, and we can measure some sort of a molarity for these, we have our choice. We can measure the change in the reactant or the change in the product with time. And there's one more notation we need to pay attention to here. We put the reactant or the product in square brackets. The square brackets indicate a molar concentration. So when we talk about the rate of a chemical reaction, much like we measure the change in position for a particular particle, we can measure a change in the concentration. And so a common unit for the rate of a chemical reaction is molar per second. Now, molarity is moles per liter. So molars per second is moles per liter per second. And then your authors start to do something here that they do for the rest of the textbook. Instead of writing numerator, denominator, the quantities that are in the denominator are given a negative exponent. And so molars times reciprocal seconds, molars times seconds to the -1, or moles times liters to the -1 times seconds to the -1. And so this is a new notation. You probably had to deal with it before in your algebra courses, but now your authors start to use it pretty extensively. And so we need to recognize our units for the rate of a chemical change is the change in molarity with time, molars per second, moles per liter per second, molars times seconds to the -1 power, moles times liters to the -1 power times seconds to the -1 power. And so we just have to get used to seeing it that way because this is how your authors start to represent. All right. So now that we recognize what we measure in order to represent the rate, the units that we're going to use, let's talk about writing a representation for the rate itself. And so we start with what is called the rate expression. Rate expression can be written for any reactant or any product in a balanced chemical equation. So let's start generally. If we have R moles of R reacting to form P moles of P, in order to write the rate expression, we would say that rate is equal to the reciprocal of the molar coefficient, so 1 over R, times the change in concentration of R with time. On the product side, we would write the reciprocal of the molar coefficient times the change in product. Now there's one more wrinkle that we have to take into account. The reactant is disappearing. And so the rate of change for the reactant is going to have a negative value. But we always want the rate to be positive. And so if we put a negative sign in front of the reactant expression, then that will give us a positive overall value in the end. And so the rate expression can be written for any general equation, negative 1 over the molar coefficient of the reactant times the change in concentration of the reactant with time, or the reciprocal of the molar coefficient in front of the product times the change in concentration with time, right? If we have a more complicated reaction, that just means we have a greater number of reactants and products to choose from that we can write our rate expression for. So the rates for this particular reaction, written as a rate expression, would be equal to negative 1 over molar coefficient A times the change in concentration of reactant A with time. Or we could write it in terms of reactant B. So again, because it's a reactant, negative reciprocal of the molar coefficient B times the change in concentration of B with time. On the product side, I'll write it explicitly. We use a plus sign. Ordinarily, we don't put the plus, it's just understood. We understood that it was present here. The reciprocal of the molar coefficient C times the change in concentration of product C with time. Or finally, we can write the rate expression in terms of product D. The reciprocal of product D times the change in concentration with time, right? So these are general. We're going to go ahead and write specific examples next. So we'll do it for both the water reaction as well as the decolorization of dye reaction that you're studying in lab this week. To write the rate expression for this actual chemical reaction, negative 1/2 times change in concentration of H2 with time. Here, 1 in front of the oxygen, 1 divided by 1 is just 1. So negative change in the concentration of O2 with time. And then on the product side, positive, but still the reciprocal of the molar coefficient. Times the change in the concentration of water with time. Now, what is our concentration actually measuring here? Well, typically we would run this reaction in a container of known volume. For convenience, let's say it's exactly 1 molar. Therefore, whatever amount, however many moles of hydrogen, oxygen, water we have, that would also be the molarity for that particular reaction. And so the molar concentrations here are not necessarily thinking of the way that we make an aqueous solution, but rather the fact that if we have a number of moles in any volume, we can calculate the molarity for that particular volume. All right, it's always just moles per liter. And then in lab, you're doing the reaction where you're taking a dye and you're putting it into an aqueous solution of hypochlorite anion. In the course of this chemical reaction, the oxygen is transferred from hypochlorite to dye. And so we get the oxidized dye molecule. I just call it DIO. The other product is the chloride anion. For this particular equation, everything gets a molar coefficient of 1. And so we have rate is equal to negative change in the concentration of dye with time, is equal to negative change in the concentration of bleach, hypochlorite anion, with time, or positive change in the concentration of DiO with time, and then finally positive change in the concentration of chloride anion with time. And so we could measure any one of these variables and would be able to talk about the rate of the overall reaction. The reason we choose the dye is because all of the other chemical species are colorless. And so the easiest metric to follow here is the metric that changes color. And since everything else is colorless, if we measure how long it takes for the dye to turn colorless, then we have the rate of this chemical reaction. And according to this rate expression, the rate at which the dye decolorizes is exactly equal to the rate at which the bleach gets used up, is exactly equal to the rate at which the DiO is formed, is exactly equal to the rate at which the chloride ion is formed. And so the rate expression gives us a handle on what the rate of this reaction would be. All right. So let's introduce two new types of chemical reactions. We don't have to worry about these in Chemistry 111, but they're going to be used as examples several times over the next couple of chapters. So therefore, it's helpful for us to be able to recognize them. The first of these is isomerization. So this is the process of changing the isomer. Now, A and B are said to be isomers of each other if they both have the exact same chemical formula. The word isomer is Greek. Mer means unit. Iso, the same or equal. And so two chemical substances that are isomers of each other are equal units. They both have the exact same chemical formula. Now, one of the classic examples of this is a molecule called propene turning into cyclopropane. So, the prefix or the portion of the word prop means that we have 3 carbon atoms. So in both of these cases, in order to have the same chemical formula, they both have to have 3 carbons. Now, cyclopropane, even if we don't know what it is, we can reason for it. Cyclo suggests that all of these carbons are connected together in a ring, just like benzene. All 6 carbon atoms were attached to each other in a ring. And so if we have 3 carbons in a ring, Notice that within the ring, each carbon already has 2 atoms to it. Carbon atoms require 4 bonds, and so that means that each one of these carbon atoms requires 2 more bonds. Well, this is a hydrocarbon, so those other bonds are going to be hydrogen atoms. And so the chemical formula for cyclopropane is C3H6. Because cyclopropane and propene are isomers of each other, they have to both have the same chemical formula, the same chemical unit. And so propene also has to have the chemical formula C3H6. Now, the attachment is what differs between these 2 molecules. For propene, the 3 carbons are laid out in a straight line. There's no cyclo. Further, this -ene suffix tells us that there is a carbon-to-carbon double bond. Remember, in benzene, we had alternating carbon-to-carbon single, carbon-to-carbon double bonds. And so it doesn't really matter which one, but one of these bonds between the 2 carbon atoms has to be a double bond. As soon as we do that, we now have 2 bonds to the carbon on the left, which means that it needs 2 more carbon atoms bonded to it. The carbon in the center has 1, 2, 3 bonds, so it requires a bond to another carbon. And then finally, the carbon on the right has 1 bond so far. We have to get it up to 4. And so if we put 3 hydrogens around that carbon, it now has 4 bonds to it as well. And if we count them up, we have 2, 3, 4, 5, 6. C3H6, C3H6. These 2 chemical substances are said to be isomers of each other. And the process where nature changes from one isomer to the other is referred to as isomerization. So in an isomerization reaction, we can just write it as isomer A converting into isomer B. Now, in your textbook, they have a representation of this. So let me call your attention to figure 16.6 on page 696. So figure 16.6, actually 16.6a on page 696. They actually show this as a reaction between methane and oxygen, or I'm sorry, ethylene and oxygen to make carbon dioxide and water. But it turns out that the shape of our plot is going to be exactly the same if we talk about the isomerization reaction. And so for the isomerization reaction of A turning into B, if we measure the concentration of A and B versus time, we start off with all A, no B. And as the isomerization process occurs, A is converted into B at the exact same rate that B is converted into A. And so just like the picture in figure 16.6b on page 696, well, I'm sorry, 16.6a on page 696, what we see here is the rate of production of B is exactly equal to the rate of loss of A. And so this particular plot would also match if we were measuring the change in concentration of di and hypochlorite versus chloride and DiO. So anytime that we end up with a chemical reaction where all of the molar coefficients are the same, whether they're all 1s or all 2s, here, molar coefficient of 1 in each case, that tells us that the rate at which A gets used up is exactly equal to the rate at which B is formed, right? So that is what we refer to as an isomerization reaction. The other reaction that is new in Chemistry 112, but we use it a lot over the next several chapters, is where two atoms of A combine to make a chemical substance B. Now, B is nothing more than a diatomic version of A. And so this particular reaction type is called dimerization, making a molecule that is two of the same type of atom. We can do the same sort of plot that we just did for isomerization. We can do this for dimerization. We start off with A, no B until we start to produce it. And so two A's are going to combine together to make one B, which means that A disappears twice as fast as B is made. And so what we see is a much steeper downslope if we're using two A's to make one B. And then the slope of B should be just like B over here. So A gets used up twice as fast. That's how we would see that represented graphically. This is the picture, now sort of, for figure 16.6b, but there we end up making the product twice as fast as we use up the reactants. So the bottom line here is the steeper slope tells us which one of these two ingredients is either being used up more quickly or is being generated more quickly. And so we now add two more reaction types to our stable. We have isomerization, and we also have dimerization. From a kinetic standpoint, isomerization has the exact same rate, loss of A, production of B. For this reaction of dimerization, we lose A twice as fast as we make B. And so these are some of the considerations now that we want to take into account as we talk about these different types of chemical equations. Well, while I start erasing this other board panel, I'm going to ask you to go ahead and open your textbooks to figure 16.5 on the top of page 695. So figure 16.5 on the page of top of page 695. Now, what they are attempting to show us here are the different types of rates that we can measure. And so we're still plotting the molar concentration on the y-axis. We're plotting time on the x-axis. And what I'd like you to recognize about this particular plot, it has a parabolic shape. We'll make more sense of the parabolic shape either tomorrow or when I get back. But the bottom line here is we can measure the rate of this reaction at any point in time. Right? Now, the rate that you're measuring in lab this week is what we call an average rate. You go from the starting point until all of the chemical has been completely converted. And so what you measure is the change in concentration from full color to no color, and how many seconds that takes to occur. So that is what we call an average rate. The average rate is useful, but it's not the best choice. It's just the easiest one to measure. Another type of rate that can be measured is the rate at any particular instant. That type of rate is called instantaneous. Because we have a plot that is curved, in order to be able to figure out what the slope is at that point would require calculus. Would have to take the first derivative, blah, blah, blah. However, we have an algebraic method for doing this as well. If we draw a tangent line to the slope, then we can calculate what the slope of that line is as the change in y divided by the change in x. And so the slope of the line at that point is the instantaneous rate. And so we actually have you calculate this in several of the activities that you do with kinetics. So the slope of the line there is equal to the rise over the run. That is the change in y divided by the change in x, which would be y2 minus y1 divided by x2 minus x1. And of course, because we have concentration on the y-axis, that would be the change in concentration of whatever metric we are following, divided by the x variable, delta t. And so, again, we have our units, molars per second, or molars times reciprocal seconds, seconds to the -1. Now, the third type of rate that we can measure is the one that is actually most frequently used. It is measured within the first 10 seconds. And I'd like you to notice that the tangent line here is nearly the same in all directions. And so this is rate type number 3. We call it the initial rate. The initial rate has to be measured within the first 10 seconds that the reaction itself starts. And it turns out that that initial rate is going to be the most important one that we have to work with. So figure 16.5 on page 695, a plot of concentration versus time, shows us that we can measure the average rate like you do in lab. We could obtain an instantaneous rate by drawing a tangent line and then calculating the slope of that tangent line. Or we can measure the rate within the first 10 seconds of the reaction starting. That type of rate is what we call the initial rate. All right, one more thing before I let you go. We've got about maybe 2 minutes, so let's take advantage of it. Although the rate expression is helpful, the really important information about the rate of a reaction is contained within what we call the rate law. The rate expression could be written for any reactant or any product. The rate law, for our purposes here in Chemistry 112, is only written in terms of the reactants. So we will not include the products. Sometimes your authors do this in the textbook. We will stay away from those situations. I just want you to start to be comfortable with kinetics. I don't want to overwhelm you. And so we're going to write our rate laws only in terms of the reactants. We're also always going to use the same format. Rate is equal to K times the concentration of reactant 1 raised to the nth power times the concentration of reactant 2 raised to the nth power. Typically, we only work with chemical reactions that have a maximum of 2 reactants, so we can stop here. But the idea is, in order to write the rate law, we write it in this particular format. Rate is equal to K times the concentration of each reactant raised to the nth power and the nth power. And lowercase k here is what is referred to as the rate constant. And so the rate is going to be proportional to the concentrations that we have for any reactant. In order to turn that proportionality into an equivalence, we introduce the scaling constant. Here, the scaling constant that we introduce is called the rate constant. Now, very quickly before I let you go, for 2H2 plus O2 turning into 2H2O, we've already written the rate expression. The rate law would be written as rate is equal to K times the concentration of H2 raised to the nth power times the concentration of O2 raised to the nth power. We don't know what M and N are. That's what we'll learn to work with tomorrow. For right now, I want you to recognize the rate law that we just wrote is in the exact same format as the general format that we just wrote. All right, we'll pick up there tomorrow. Hope everything's going well with lab, etc. Let me go ahead and end the recording. And I look forward to seeing you all very soon.